In section 1.4, we will study 4 topics: independent events, properties of independent events, mutual independence of 3 events, and finally distinguish the 2 concepts: independence and mutual exclusiveness, are also called disjointness of 2 events. Okay, now let's start the first topics: independent events. It is natural to say that the 2 events A and B are independent if the occurrence of one of them does not affect the probability of the occurrence of the other one. So in terms of probability notation, we can write probability of A given B already occurred is the same as probability of A. That means knowing B already occurs does not affect the probability of A occur. Or we can also say probability of B occur given A already occurred is the same as probability of B, which means knowing A already occurred does not affect the probability of B occurs. So if we combine, say, one of the above condition, say this one, probability of B given A occur already is the same as probability of B. Combine this with the multiplication rule, we can conclude that the probability of the intersection of A and B is the same as the product between the probability of A and probability of B. So how do we do that? So by the multiplication rule, we have this equation. Probability of A intersect B is equal to probability of A multiplied to probability of B given A. Now, knowing that probability of B given A is the same as probability of B, we can replace the probability of B given A by probability of B. So there we arrive the conclusion. Probability of A intersect B is the same as probability of A multiplied to probability of B. So similarly, if we have probability of B given A is the same as probability of B, also by using multiplication rule, we can also derive the same equation. Probability of A intersect B is the same as probability of A multiplied to probability of B. Vice versa, if we are given this equation, and suppose that probability of A intersect B is equal to probability of A multiplied to probability of B, we can also prove that probability of A given B is the same as probability of A, and probability of B given A is the same as probability of B. We can do this by just simply using the formula to compute the probability, the conditional probability of A given B, and then apply this given information. Here is what we had in the previous slide about 2 independent events. 2 events A and B are independent if any of the following holds. The probability of A occur given B already occur is the same as the probability of A occur, or probability of B occur given A already occur is the same as probability of B occur, or probability of A and B, both A and B occur, which is the intersection of A and B, is the same as the product of probability of A occur and the probability of B occur. Let's take a look at some examples. In the first one, we have 2 independent events, A and B. with probability of A occur is 0.4 and probability of B occur is 0.5. We want to compute the probability of both A and B occur, which is the probability of intersection A intersect B. So because we know that both the A and B are independent, so the probability of A intersect B is the same as the product of the probability of A and the probability of B. And we are given probability of A is 0.4 and probability of B is 0.5. Therefore, we have 0.4 times 0.5, which is 0.2. Now, how about probability of A union B? That means either A occur or B occur or both. Then we have the formula. This union, the probability of the union is the probability of A plus probability of B, subtract the probability of the intersection. And all of these three probabilities are now known. Probability of A is 0.4, probability of B is 0.5, and probability of the intersection of A between A and B is 0.2, which we just found in the previous question. So we have 0.4 plus 0.5 minus 0.2, which is 0.7. In the second example, we will draw a card from a deck of 52 cards and then replace it back. Then draw the second card. We are interested in two events: getting a queen on the first draw and getting an ace on the second draw. The question is if they are independent. So intuitively, we expect these two events are independent because we already replaced the first card back. So that means the probability of getting the ace on the second card should not be affected. But we still need to check carefully using the definition of the two independent events. And remember, we have three different ways to verify independence of two events. But let's see what we need in this case. So again, we'll assign names to relevant events in the problem. So we call Q1 to be the event getting a queen on the first draw, and A2 to be the event getting an ace on the second draw. So it is very clear that the probability of getting an ace on the second draw, given that getting a queen, we got a queen on the first draw, will be 4 over 52. Because after we draw the first card, we replace it, so the deck is still have a full 52 cards, and we still have all 4 aces. So the probability of getting an ace the second time we draw a card from the deck is clearly 4 over 52. So next we will want to check if we want to find probability of A2, because we want to verify if the probability of A2 given Q1 is the same as probability of A2. If that's the case, then that means the two events are independent. Okay, so how do we find P of A2? In this case, a tree diagram is actually quite useful to see the whole experiment. So we need one more notation. We call A1 to be the event getting an ace on the first draw. So with that notation, we can fill in this tree diagram. That is the root. So the first draw we get either an ace or not an ace card. with the corresponding probability to be 4 over 52 and 48 over 52. Now on the second draw, we remember we replace the ace we draw. If we start from here, that means the first draw was an ace. So if we replace the ace back, we still have a full 4 aces in a full deck. So the probability of A2 given A1 is still 4 over 52. And the other probability that A2 prime, remember A2 prime is the complement of A2, which means it's not an ace card. Given A1 is 48 over 52. So similarly, we can fill in these two branches. This will be no ace here. So if we replace this no ace back, this probability of getting an ace the second time is still 4 over 52, while the probability of getting a non-ace card is still 48 over 52. We are interested in finding the probability of A2. That means these two outcomes are of our interest here. So to compute this probability of A2, we can follow the branches which lead to A2. So we have two paths here. Okay, this one and then this one. And along the same path, we just simply multiply those probabilities together. We can also see that if we write the probability of A2 as the probability of A1 intersect A2 plus probability of A1 prime intersect A2. This means the first time we draw an ace and the second time also an ace. And this means the first time is not an ace and the second time is an ace. So then if we use the multiplication rule for each of these probability, we will have these two products. And these two products are displayed along the paths here. So these two are here and these products are displayed along this path leading to A2. So we just now plug in those values of those probabilities. So PA1 is 452, PA2 given A1 is 452, and probability of A1 prime is 48 over 52, PA2 given A1 prime is 4 over 52. So after we simplify, we will get 4 over 52, which is actually the same value as the probability of A2 given Q1, which we discussed earlier here. So because probability of A2 given Q1 is the same as probability of A2, then we can say these two events are independent. On the next example, this is similar to the previous one, except this time we will not replace the first card back into the deck. We still draw two cards, but do not replace the first one back to the deck after we draw it. And still the same question. Are the event of getting a queen on the first draw and the event of getting an ace on the second draw independent? So everything are quite similar, except we have to make some adjustments along the way. So still call Q1 to be the event of getting a queen on the first draw, A2 to be the event of getting an ace on the second draw. Then it is clear that we have this condition on probability. If we draw the first card to be, if the first card is a queen, then the probability of drawing an ace the second time will be 4 over 51 because we did not replace the card back to the deck. So the deck now has only 51 cards. And among those cards, there are still 4 aces. So this probability, this conditional probability is clearly 4 over 51. We will compute P of A2 to see if this equation holds. If it is, then the two events are independent. So again, we have another tree diagram, and we need to make some adjustment on the second branches here. Okay, the first one still 4 over 52 for drawing an ace, and 48 over 52 for not drawing an ace or drawing a non-ace. Now, this probability, which is getting an ace the second time, given that the first time also an A, this time it will be 3 over 51 because again the deck now has only 51 cards with 3 aces still in this, is still among these 51 cards. And this branch here, the probability will be 48 over 51. Now this branch, the probability will be 4 over 51 because the first time we did not draw an ace. So there are still 4 aces among the 51 cards. And here should be 47 over 51. So now again we are interested in these two outcomes, A2, A2 here. So we multiply the probabilities along the same path. We have 2 paths leading to A2, and those again are shown here. So we get 4 over 52 multiplied to 3 over 51 plus 48 over 52 multiplied to 4 over 51. And after we simplify this, again we get 4 over 52. And remember, the conditional probability of A2 given Q1 is actually 4 over 51. It's slightly larger than 4 over 52. So in this case, these two probabilities are not the same, which means that Q1 and A2 are not independent. On the next example, this time we also will not replace the card we draw the first time, and we want to say we have two different events in this problem: getting the queen on the first draw and getting a queen on the second draw. The question is whether they are independent. So this time we call Q1 to be the event of getting the queen on the first draw, Q2 be the event of getting a queen on the second draw. Then it is clear that the conditional probability of Q2 given Q1 is 3 over 51 because there are 51 cards left and with only 3 queens among them because we already draw a queen the first time. So we will compute P of Q2 to see if this equation holds. So again, with the tree diagram, or if after a while you get used to it, you actually can do it directly this way. So again, there are two outcomes we are interested in here, Q2, Q2, and these two paths are leading to those Q2. So we have here 4 over 52 times 3 over 51, okay, which is this product, and then 48 over 52 multiplied to 4 over 51 right here, which is this product. So doing the calculation, we get 4 over 52. That is probability of getting a queen on the second draw. Now, the condition on probability of getting queen on the second draw, given that the first draw we also got a queen, is 3 over 51. While this probability is 4 over 52. They are different. That means Q1 and Q2 are not independent. In the next example, we toss a fair dice twice, and we let A to be the event that the sum of the two tosses is 5, while B be the event that the dice land for the first time. We also want to know if these two events are independent. So in this case, we can actually list the members in both A and B quite easily. So we will choose to do that, and this time it will be easier to use this to verify this formula. So we will need to, because we can clearly find the elements in A, B, and then the intersection of A, B. So it's easier to verify this formula this time. So we have A will be this set because the sum of the two tosses is 5. So we can only have 1, 4, 2, 3. Cannot be any other option. And then we change the rows of the dice. So first die is 3, second die is 2, and then first die is 4, second die is 1. Now for B, what do we have? We have the dice land 4 the first time, so it has to be 4 on 4 here, and it doesn't matter what the second time the result of the second time. So we have 1, 2, 3, 4, 5, and 6. So B has 6 members, while A has 4 members. We can easily find the intersection of A and B, which contains only one element, that is 4, 1. 4, 1 here, 4, 1 here. And the total numbers of possible outcomes is clearly 36, because every time we have 6, we have 2 times, it will be 6 times 6 using the multiplication rule or the multiplication principle. So since A intersect B has only one element, the probability of A intersect B is number of favorable outcome, which is 1, over the numbers of all possible outcomes, which is 36. So we have 1 over 36. Then PA will be 4 over 36, which is 1/9, and the probability of B is 6 over 36. Then we can put them on into this equation and see if they are the same. So on the left hand side we have 1 over 36. On the right hand side we have 1/9, which is probability of A, and probability of B, which is 1/6. So we have 1 over 54. These two numbers are different. That means A and B are not independent. In example 6, we also toss a fair dice twice, and let A to be the event that the dice lands 4 the first time, and B be the event that the dice lands 5 the second time. We want to know if A and B are independent. So intuitively, we feel that these two events should be independent, because landing a 4 the first time really should not affect landing a 5 the second time. But let's see if our intuition is correct this time. Okay, we need still to check that feeling mathematically. So we need to verify if this equation holds true. So similar to the previous example, we can find all of the members of A and B, with A being the event that the dice land for the first time, we have these 6 members. And with B being the event that the dice land 5 the second time, we have another 6 members. So the intersection of A and B has only one member, which is 4, 5. Okay, 4, 5 here, 4, 5 here. So the probability of A intersect B is 1 over 36, while the probability of A is 6 over 36, since A has 6 members. Similarly, probability of B is also 6 over 36, which is 1/6. So we can verify that the product of probability of A and B is the same as the probability of A intersect B, because both of them are equal to 1 over 36. Therefore, we can conclude that these two events are independent.